everyone, this is a video for class 23 of PH 125. Today we're going to be continuing to talk about torque and angular acceleration, and we're also going to introduce angular momentum. Okay, so just a quick reminder on torque. Remember, torque is really just the rotational effect of a force. So if you think about, for example, having a wrench here, which is on a bolt, and you apply some force, which is along the direction indicated by the blue arrow, to the arm of the wrench. Okay, then it turns out that the torque, or the rotational effect of that force that you're applying, is going to be equal to RF sine theta. R is the magnitude of the distance from the pivot point, so the point about which your rigid body is rotating, to the place where your force is applied. So that's going to be the distance R. It's always a positive value. Okay, then F will also be just the magnitude of the force. And then sine theta, theta is really the angle between R and F. Okay, so this is how we calculate the torque. And then we could alternatively define what's called the perpendicular lever arm, or perpendicular moment arm, R perp. And so R perp is really just the perpendicular distance from that pivot point to the place where your force is applied. Really, it's like the perpendicular distance from the force line, if you extend the force line outwards, and then somehow draw a line perpendicular to that force line that goes through the pivot point. It's the distance from the pivot point to the force line along that, perpendicular line that you've drawn in. So that would be indicated with this green line here. Okay, so in that case, if you look at that green line, you can see that it is the opposite to the angle theta that's drawn in here. And so what that means is that we could say that sine theta is equal to R perp divided by R, the hypotenuse, or rearranging, we get R perp is equal to R sine theta. Okay, so then we recognize that we also have R sine theta in our torque equation here. And so what that means is that we could rearrange and say that the torque is really just equal to that perpendicular lever arm multiplied by the force F. Okay. So then just a few more notes on torque. Remember, it has units of newtons times meters. And the direction of torque is generally positive if it's counterclockwise, if it causes a counterclockwise rotation, and it's negative if it causes a clockwise rotation. Okay, and then it's really important that you always define the axis of rotation about which the torque is rotating. Okay, and so then remember that force is a push or a pull, and it's something that causes a linear acceleration. When applied to an object, it causes that object to accelerate linearly. And now, because the torque is a rotational effect of a force, what that means is that torques are going to cause rotational acceleration. Okay, so what that really is telling us is, in terms of vector components, we know that the net force in the x direction is equal to the mass of the object times its acceleration in the x direction. And this is really, the net force in the x direction is just the sum of the x components of all the forces acting on your object. And similarly, we could define F net y is equal to MAY, and it's going to be the sum of all the y components of the forces acting on your object, which has mass m. All right, and so then the new piece is really that the sum of the torques acting on the object, or in other words, the net torque acting on the object, is equal to I alpha, where I, remember, is the moment of inertia of your object, and alpha is that rotational acceleration. Okay, and then we can calculate the net force acting on an object by summing up all the torques that act on that object. Torque, remember, is of course force times that lever arm times sine of the angle between the force and the lever arm. And so you'll have to calculate that out for each force acting on your object. A few notes on calculating these sums. Remember that when you do the sum of the forces, whether it's in the y direction or the x direction, you always want to make sure that you're including the direction of the force in the x or y direction by including a plus or minus sign, right? So normally we would say plus is going to be either to the right or up, and negative is going to be to the left or down, depending on if you're talking about x or y. Now we want to make sure we're applying our convention for the torques as well. So you would want to assign a positive torque if it causes a counterclockwise rotation, and you would want to assign a negative torque if it causes a clockwise rotation. Okay, so that's going to be the new piece here. But otherwise, you'll want to do the same sort of method as before. thinking about, do I have an acceleration? Do I have an acceleration in the x direction, the y direction? Do I have rotational acceleration, right? So now we have three pieces to think about. And then using these relationships to relate those accelerations, whether it's linear in the x or y direction, or if it's angular, a rotational acceleration, then we want to relate those to the forces acting on the object or the torques acting on the object. Okay. So now we want to talk about a very specific case. This is a case that we'll encounter very often, and this is a static equilibrium. So this is something that you'll look for in the problem statement. The object is at rest, or it's balanced, or it's moving with constant velocity or constant angular velocity. Any of those will tell you that we have a situation for static equilibrium. So when we have static equilibrium, what that means is that the net force acting on the object is zero. And specifically, that means the net force in both the x and y directions individually are both equal to zero. And because we have no rotational acceleration either, that means that we have the net torque acting on the object is also equal to zero. Okay, and so then you'll want to sum up all the torques acting on the object, set that sum equal to zero, sum up all the forces acting on the object in the x or y direction, and set those both equal to zero as well. So this is the same method as I just described on the previous slide, except this is this specific case where we don't have to worry about the acceleration, whether it's angular or linear. In both cases, it will just be zero. So this is a little bit of a simplified version of the problem that we were just talking about on the previous slide. All right, so when these three conditions are met, that's when we have static equilibrium. And remember, it can be a little bit tricky to think about defining the torques, because when you have an object that isn't rotating, it's harder to think about what the axis of rotation is. So it turns out in these problems, you can pick the axis of rotation to be anywhere, but there is usually a convenient location. So whenever you have one of these problems and you have two forces that you don't know, and one of them is something you're not looking for, that's where I would pick my pivot point so that the torque due to that unknown force that we don't really care about goes away in our sum of torques equation. Okay. So the strategy for these problems then, we mentioned this last time, you always want to start by drawing a free body diagram that helps you with understanding the forces that are acting on your object. And as I mentioned last time, instead of the traditional free body diagram, when you have one of these rotational torque situations, static equilibrium, so something where you're thinking about torque and not just forces, it's convenient to do like an extended free body diagram so that you are drawing in the forces and then also making note of where the forces are acting relative to some pivot point, some origin, something like that, so that you're taking those into account when you're drawing your free body diagram. All right, then we'll also want to use the fact that the sum of the forces in both the x and y directions are zero. Choose your pivot point so that you can define the distance from the pivot point to the place where each force is acting, because then we're going to write out the fact that the sum of the torques is also equal to zero. So we'll need those distances to the individual forces to do this sum of torques equals zero equation. All right, and so then once you're done with that, you will have many equations relating your unknowns, and you should be able to solve for the thing you're looking for. Let's do a practice problem here. So here we have a grocery cart, well, not a cart, I guess, a basket. It's 62 centimeters long, and so far you've placed a 1.8 kilogram carton of milk at one end, a 0.72 kilogram box of cereal at the other, and we want to know where you should place a 1.75 kilogram carton of orange juice to balance the basket. Okay, so there's that keyword we were looking for, balance, right? So that tells us immediately this is a static equilibrium problem. And so what that means is that the sum of all the forces acting on the basket must be zero, and the sum of all the torques acting on the basket must also be zero. Okay, so let's start by drawing a little free body diagram here. I'm going to simplify things a little bit. Here's my basket, and we know that there's a handle that's at the middle of the basket. So let's say that we have some F handle here. All right, so that's the force of you pulling up on the basket, right, to keep it off the ground. Okay, so that's F handle. Then we know that we have a 1.8 kilogram carton of milk at one end. So let's go ahead and draw my carton of milk. Let's say it's over at this end. And so then we know that its weight is going to be pulling downwards on the basket over here. So let's call this FG milk. And we know that its weight is going to be M milk, which is 1.8 kilograms, multiplied by the acceleration due to gravity. Okay, so that's the weight of the milk acting at one end of the basket. And then at the other end, we've placed a 0.72 kilogram box of cereal. So let's put our cereal over here. Its weight will also push down on the basket. And so we'll have FG cereal, which is going to be equal to the mass of this cereal, 0.72 kilograms, times the acceleration due to gravity, g. Okay, and so now we want to know, where do we place the orange juice to balance the basket? All right, so looking at the situation right now, I have a heavier object on the left-hand side of the basket than on the right-hand side, so I'm going to guess that it should be somewhere on the right-hand side, but we don't know where. So I'm just going to go ahead and draw it in over here and say that this is going to be FG of my OJ. All right, and we also know what FG of the OJ is. I don't have room to draw it, so I'll just write it down here. FG of the OJ is equal to its mass, which is 1.75 kilograms, and that's going to be multiplied by g to give us the weight of the orange juice. Okay, so we have all of our forces labeled, and we are ready to think about the sum of the forces acting on this basket. Okay, so F net, it must be equal to 0 if our basket is balanced. It's not accelerating upwards or anything like that. And so that tells me that it's going to be the sum of all the forces added together must be 0. All right, so what do we have here? We have the force of the handle upwards. And really this is all in the y direction. So F handle. And then in the negative y direction, we have minus FG milk. I'm going to shorthand it FGM. Minus FG of the cereal, let's call it FGC, minus FG of the OJ. Okay, all right, so those are our sum of forces here. And that really doesn't tell us that much. We actually already know all of our weights of all of our different objects. So really all this is telling us right now is that the force exerted by the handle has to be equal to the sum of the weights of the 3 objects in our basket. So that's great, but that's not the piece of information we're looking for. What we want to know is where we're supposed to place our orange juice to balance the basket. So this particular equation doesn't really help us this time. So what we want to think about then is the sum of the torques. And so to do that, we should start by defining a pivot point. I'm going to go ahead and pick my pivot point to be at the handle here. So I'm picking that because we don't have the force of the handle. We could calculate it, but that's an extra step that we don't really want to do. So let's pick the pivot point to be right at that handle, and that way the torque due to the handle will just be 0, since it's going to be at a lever arm, a distance r of 0 from the pivot point. So this is my pivot point. All right, and so now we're ready to think about the distances to each of the applied forces. So those are those r values. All right, so let's go ahead and start with the milk. So r for the milk, let's call it RM. All right, and so we know the distance, we said the entire basket is 62 centimeters long. And so that means that half of the basket is going to be 31 centimeters. And so the distance from the handle to the milk should be 31 centimeters or 0.31 meters. Okay, so that's going to be R for the milk. Next, we want to think about R for the orange juice here. That's our question mark, right? That's the thing we're looking for. So ROJ, that's the thing we're looking for. We don't know it. And then lastly, we can define the distance from the pivot point to the cereal. And that's what we would call, I would call it RC. And we know that that distance is also 0.31 meters, right? Because the cereal is at the other edge of the basket. So since the basket is 62 centimeters long, it should be at 31 centimeters. Okay, so those are all of our lever arms. Last thing we want to think about all of our angles, right? So what are all of the angles between R and F? So here we have a nice situation. All of our forces are directly downwards. They're all in the negative Y direction. All of our lever arms are in the X direction. So the lever arm for the milk is in the negative X direction. The lever arms for the orange juice and the cereal are both in the positive X direction. So what that means is that in all three cases, the angle between the force and the lever arm is 90 degrees. So we end up getting sine of 90 degrees in each of our torque equations, which is just 1. So then we end up with torque that's just equal to R times F in each of these three cases. And I should also mention here that our handle is equal to 0, right? Because that's where we chose our pivot point to be. All right, so now let's go ahead and define the sum of the torques here, tau net. The sum of torques has to be equal to 0, and it's equal to the sum of the torques acting on the basket. So first of all, we get 0 times the force of the handle, right? So that would be the torque due to the handle. And so that whole first term is 0. All right, next let's think about the torque due to the milk. Okay, so here we have the torque due to the milk. If you think about, for example, holding your pencil at the middle and then pulling down at the left-hand side corresponding to the place where we've put our milk. So if you pull down on the left-hand side, that would cause a counterclockwise rotation of your pencil. And so similarly, I would say that that causes a counterclockwise rotation of the basket. And so that torque is going to be positive. All right, so let's say it's going to be plus R milk times FG milk. All right, next up we have the torque due to the orange juice. And so again, thinking about holding your pencil at the center and pulling down now on the right-hand side, because the orange juice is on the right-hand side of the pivot point pulling down, I would get a clockwise rotation of my pencil. And so I would say that that's a negative torque. So I would get minus then the torque due to the orange juice, which is going to be ROJ FG OJ, and then times sine of 90 degrees, which is just 1. And then finally, we have the torque due to the serial. Once again, it's on the right-hand side of the handle, right-hand side of the pivot point. And so that's going to, again, cause a negative torque. So we get negative R serial, FG serial, and once again, it's times sine of 90 degrees, which is just 1. Okay. So this is great. Now we have all the information we need, and the only thing we're missing is ROJ, which is what we're looking for, which is wonderful. So let's go ahead and solve for ROJ here. I'm going to add ROJ FG to the other side and then divide by FG of the OJ. So we end up with R of the OJ is equal to RM FG of the milk minus RC FG of the cereal, and then we would divide all of that by the weight of the OJ. Okay, and so now we actually have all of this information over on our free body diagram. And so we could plug in all of our values, right? So we have our milk is 0.31 meters. FG for the milk is going to be 1.8 times G. RC is 0.31 again times FGC, which is 0.7 kilograms. Oh, sorry, this should have been 0.72. I apologize for that. So this should be 0.72 kilograms times G. And then finally, we know that we can divide by the weight of the OJ, which is 1.75 kilograms times G. Okay, and so when I did that, I got ROJ is equal to 0.19 meters, or in other words, it's 19 centimeters. Okay, and so then we would want our R of the OJ to be positive 19 centimeters from the pivot point. And so that means that we did draw our arrow on the right side. So we drew the weight of the OJ on the correct side to balance the basket. If we had drawn it on the wrong side, we would have just gotten a negative value there. Okay, that's great. It's about halfway. It's not quite half. It's a little bit more than halfway, but about halfway then between the handle and the edge of the basket. And so now we want to talk a little bit about angular momentum. So just a quick reminder, linear momentum P is equal to mass times velocity, and it has units of kilograms meters per second. And remember that a force causes a change in linear momentum. This is that modified version of Newton's second law. We get F equals delta P over delta T. And so what that means is that if you have no net external force acting on a system, remembering that the internal forces will always all cancel, then that means that we get a delta P over delta T equal to 0, or in other words, the change in momentum is 0. So we could say then that P final is equal to P initial in those cases. So we use this a lot in terms of like collisions. Remember that was always true, that there were no net external forces acting on the system, and so we could use conservation of momentum to solve those problems a bit more easily. All right, so now we want to think about angular momentum. So to do that, we're going to consider a point particle that's in uniform circular motion, which just means that it's moving around in a circular path with some constant speed v. All right, and so let's start with linear momentum. So what's the linear momentum of that particle? If it has mass m and it has speed v, it's going to be m times v. That's the magnitude. And now what we're going to do is kind of arbitrary, but we've been doing this a few times already this semester. We're just going to multiply both sides of the equation by r. We can do that. We can do that as long as we're doing the same thing to both sides of the equation, it's okay. So let's just multiply both sides by r. So now we get rp equals mvr. All right, well, so now we want to remember in terms of rotational quantities that r times omega is equal to the speed v. And so what I can do is take v in my equation here, and I'm just going to replace it with r times omega. All right, so now I get r times p is equal to m r squared omega, right? Because I get r times omega. Okay, and so all I'm going to do is regroup stuff, and I have mr squared times omega. You might remember mr squared was actually the moment of inertia of a point mass in uniform circular motion, which is what we have here, right? So this was the specific case where we have a point mass in uniform circular motion with constant speed v. And so in this specific case, I is equal to mr squared. Okay, and so that means that this term in parentheses mr squared is really just I. And so what I can do is I can redefine the left-hand side of my equation, and I'm going to call that L. So L is equal to I times omega, and for a point mass, this tells us that L is actually equal to R times P. But that's only specific for a point mass in uniform circular motion. It's nice because it has that same symmetry with, remember, all of our translations between our linear quantities and our rotational quantities. So it's nice that it has that same symmetry. But in general, it's better to remember that L is equal to I times omega, since this term in the blue box is only true for a point mass in uniform circular motion. Okay, so now we have this new term here, angular momentum. L is equal to I times omega, and it will have units of kilograms meters squared per second. So the kilogram meters squared comes from the moment of inertia, and then radians per second is the SI unit for omega, right? That angular speed. So we end up with units of kilograms meters squared per second. All right, and so what is going to cause an angular momentum? Well, remember that forces caused a change in momentum with respect to time. Well, it turns out that torques will cause a change in angular momentum with respect to time. So we have this relationship tau is equal to delta L divided by delta T. And this is important because if we have no net external torque acting on an object, then we will have conservation of angular momentum. Just like when we had no net external force acting on an object, we had conservation of linear momentum. So that means if the net external torque acting on a system is 0, its final momentum is going to be equal to its initial momentum in terms of angular momentum L. All right, let's do some practice here. So we want to start by just thinking about angular momentum. We have a figure skater who's spinning at a rate of 12.5 revolutions per second with her arms in by her sides. And when she's doing this, when she has her arms in by her sides, her moment of inertia is 0.64 kilograms meters squared as she rotates around. And we want to know what is her angular momentum. Okay, so we have some known quantities here. First, we know that her moment of inertia, I'm going to call it I sub I for initial because it's about to change in the next part of the problem, is 0.64 kilograms meters squared. And she's rotating at a rate, let's call it omega initial, of 12.5 revolutions per second. Okay, and so revolutions per second, that's fine, but let's convert into radians per second. That's the SI units for omega. So to convert, we're going to remember that there are 2 pi radians in every revolution. Okay, and so when I calculated that out, you get 25 pi radians per second. So you could convert it out. You could multiply the pi through if you want to. I like to leave things in terms of pi. Usually the numbers are a little bit nicer. Pi is, you're always going to have decimals when you have pi. So you can just plug in the pi at the very end. It's what I would recommend doing. Okay, and so then our question, what we're looking for here is the angular momentum L. All right, so L, remember, is equal to I times omega. Here it's specifically going to be the initial moment of inertia times the initial angular velocity, omega. Okay, and so we have those two numbers. We just plug them in. So we get I is 0.64 kilograms meters squared times omega, which is going to be 25 pi times radians per second. Okay, and so we see that we do in fact here get kilograms meters squared per second, which is good. And when I calculated that out, let's see what I got. 16 pi kilograms meters squared per second. Or if you want to multiply the pi in, I got 50.3. It rounds up, 50.3 kilograms meters squared per second. Okay, so that would be my momentum here in the initial case where her arms are in by her sides. And now we want to say, okay, now she stretches her arms out to the side and her moment of inertia changes to some new value of 2 kilograms meters squared, and we want to know what's her new angular speed. So this means that I final is going to be 2 kilograms times meters squared, and omega final is what I'm looking for. So how am I going to relate these two situations? The key is going to be thinking about the fact that, remember, a torque causes a change in angular momentum. So that means that here we want to think about what's the net external torque acting on her. So what is tau net external? That's really what we want to know, because remember, tau net external is going to be equal to delta L divided by delta T. Okay, so what is that net torque, external torque acting on her? Well, what external forces are acting on her? Only gravity, right? That's the only thing that's going to be acting on her. Also, a normal force, keeping her on the ice, but those two things will cancel out. And so then I would say that the net external torque acting on her is going to be 0. So there's going to be no net external torque acting on her. There's no net external force acting on her at all. Okay, so that's equal to 0, and so that tells us then immediately that the angular momentum is going to be conserved, right? So there's no change in angular momentum. L final is equal to L initial. All right, so now with that piece of information, we're ready to solve for the final angular speed, because we know that L final is equal to L initial, which is this 16 pi kilograms meters squared per second. Okay, and that's also going to be equal to I final omega final. And so then we can solve for omega final. It's just going to be 16 pi kilograms meters squared per second divided by I final, which is 2 kilograms meters squared. So these will all cancel. We're left with 1 over seconds, which is really going to be radians per second. And 16 divided by 2 means that we're going to end up with omega final equal to 8 pi radians per second. Or remembering that 1 revolution is 2 pi radians, this is going to be 4 revolutions per second. Okay, so that's going to be her final rotational speed. All right, now let's do a few more examples. So here we go. We're thinking you're sitting on a freely rotating bar stool with your arms outstretched and a heavy mug in each hand, and then your friend gives you a twist and you start to spin around. So you start to spin around a vertical axis through the center of the chair. All right, and so you're sitting out there, you've got your arms outstretched, and then you bring your arms in tight to your side. All right, so that's the problem setup, and you keep spinning. We want to know what happens to your angular momentum as you pull your arms in. Okay, so this problem is very similar to the skater problem that we just did. So the key to thinking about what happens to your angular momentum, in other words, does the angular momentum change? Well, when you think about that, you always want to think about, is there a net torque acting on my object? If there is, your angular momentum would change. If there isn't, then you have conservation of angular momentum. So is there a net torque acting on your object? No, there wouldn't be. This is just like the skater. So the two forces acting on your person would be gravity pulling downwards, and then the normal force pushing up. Those two things are going to be equal and opposite and cancel out. So there's no net force acting on you. There's no net torque acting on you. And so that torque is equal to 0 and angular momentum is conserved. So since angular momentum is conserved, that means that the angular momentum is C, going to stay the same. All right, next one. We want to know what happens to your angular velocity. Okay, so to answer this question, we have to remember that the angular momentum is the same as before. And then we also have to remember that piece of information about moment of inertia that I told you is like the one thing that you should really memorize out of this section. So remember that the moment of inertia is bigger when you have more mass far away from the axis of rotation. So in which case here do we have more mass far away? That would be the initial case, right? So when the mugs are far away from you, that means that you have more mass far away from your axis of rotation. And so since I final is going to be smaller, and we know that the momentum is equal to I times omega in both cases, that tells us that omega final is going to have to be bigger, right? So it's going to have to counteract the fact that I is getting smaller, so that the product of those two things, I times omega, is the same as it was before. And so that tells me that you should be spinning faster, and that's answer A here. All right, last one is the trickiest one. So this one we have to think really carefully about. So what is happening to your kinetic energy as you pull in your arms? And the trick to this one is to get the kinetic energy in terms of something you know is changing and something you know is staying the same. Because if you have it in terms of two things that are changing and one's going up and one's going down, it's really hard to tell which effect will dominate. Okay, so let's see how this one went. I know this is the tricky one. All right, so we already know that we have this fact that L final is equal to L initial, and we have I final is less than I initial, right? And so that meant that omega final was greater than omega initial. Okay, and now we already know that K is equal to 1/2 I omega squared, but I is changing and omega is changing. So this was the thing I was warning you against. It's really hard to know if I goes down and omega goes up, which will be the dominant effect. Will K go up or will it go down? So this is too hard to analyze in this form. It's not helpful to us. And so we want to get it in terms of something that's constant, which is the angular momentum L, and something that's changing. Okay, so how am I going to do that? Well, I recognize that L is equal to I times omega. Here I have omega squared, and so what I want is to get I squared as well. So I'm going to multiply 1/2 I omega squared by I divided by I. Okay, so when I do that, that's okay, because I divided by I is like multiplying by 1, so we're allowed to do that. And so then I get 1/2 I squared omega squared divided by I. So these two terms on either side of the equal sign, those are the same, so that's okay. And so then what I see is that my numerator here, I squared omega squared, that's just going to be my angular momentum L squared. So I end up with K is equal to 1/2 L squared divided by I. And now this is much easier to analyze because we have L staying the same, and I is going to be getting smaller, but it's in the denominator. So we're dividing by something smaller, which means that the kinetic energy is going to be increasing. So I would pick answer A here. All right, so that one was tricky, but hopefully you guys got there. And if not, please ask questions in class, and I will see you then.